we might just have a way to peer 13 billion years into the past. It wouldn't require a ship to travel through a black hole, nor would it require a time machine. Succeeding the Hubble telescope, which gave humanity 1.3 million observations and discoveries since its launch in 1990, is the James Webb Space Telescope. Its key mission will be to look back through time when galaxies were young and the universe had just begun. But in its journey, it will do a great deal more than that. In humanity's search for an exoplanet that can support life, the James Webb Telescope can provide vital information on the composition of the atmospheres of exoplanets. It will do that by recording atmospheres through planet movements and photograph them as they pass by bright stars. They wouldn't be sweeping panoramas, but mere dots on an inky black sheet. As the planet passes its host star, the James Webb camera will record a slight dip in light, giving an idea of the size of the planet. Recording dips in multiple wavelengths would provide us with even more information. Atoms and molecules absorb light at different wavelengths, which would give an idea of which molecules are in the planet's atmosphere. That would be perfect for detecting any molecules that are common on Earth, like carbon dioxide and oxygen. And maybe we can start thinking about mapping a course to new planets beyond our solar system. We have yet to observe the era of our universe's history when stars and galaxies had begun to form. Our universe is ever expanding, and as stated in Einstein's theory of relativity, as spaces between objects in the universe expand, the light from the first stars travel in our direction. Its waves lengthen, making the light fainter and infrared. The farther we look, the faster objects move away from us, redshifting the light. We can't see inside dust clouds, or how many planets out there would be hospitable to life, or where stars and planets are being born nearby. So to study the earliest star and galaxy formation in the universe, we need to have something that helps us observe infrared light. Unlike the Hubble, the James Webb Telescope would be able to give us information on all this. It would show us things the Hubble never could. We would be able to view the first stars and galaxies forming after the Big Bang. We can see stars and planetary systems forming inside clouds of dust that are opaque to visible light. Webb would be able to see what the universe looked like just 100 million years after the Big Bang, when the first stars and galaxies began to form. But how would it do that? The primary mirror of the James Webb Telescope is composed of 18 hexagonal mirror segments made of gold-plated beryllium, which all combine to create a 6.5-meter or 21-foot diameter mirror, considerably larger than the 2.4-meter or 7-foot 10-inch mirror of the Hubble telescope. The mirror would increase the amount of collected light. The more the light, the more detailed our image. The hexagonal shape allows the mirror to be folded on Earth and later unfolded in space. The shape also makes it possible for the segments to fit together without leaving gaps between the panels. It is also the closest possible shape to a circle, which focuses the light into the most compact region on the detectors. An oval mirror, for example, would give images that are elongated in one direction, and a square mirror would send a lot of the light out of the central region. Once the hexagonal mirror is unfolded in space, the mirror's focus would then be calibrated by shifting the various segments with an accuracy of 1 to 10,000, the thickness of a strand of human hair. The light is collected on the secondary mirror before being reflected, filtered, and then focused on the hypersensitive infrared detectors. Here, the photons are converted into electrical voltage. The telescope is equipped with 4 tools. NIRCam is the primary imager. 10 sensitive detectors allow it to detect the light of the first stars in the galaxy. NIRCam has also a coronagraph, which would allow us to view the more faintly lit stars closer to a brightly lit star, along with the exoplanets circling the star. But to capture faint light like that, the telescope would have to watch the object for over 100 hours, and even then, we wouldn't have nearly as much information about the objects as we would want. For that reason, we have NIRSpec, the second tool. It can provide spectroscopies for hundreds of objects in the matter of minutes, thanks to a micro-shutter system. The system is made of 250,000 shutters that will filter out the irrelevant light and focus on the most faintly lit object. The light is then dispersed into the spectrum and sent to the detectors. To do that, the telescope would have to be constantly directed at different targets, which it will do with the help of a fine guidance system. The third tool, star and planet formation in the local universe, happens in the centers of dense, dusty clouds obscured from the human eye. At that point, near-infrared light wouldn't be enough to penetrate through the blanket and give us the information we need. For that, the James Webb Telescope has MIRI, which is equipped with a camera and a spectrograph, but it works in a different range of infrared light, one with longer waves. And MIRI is what will help us observe the redshifted light of distant galaxies and newly forming stars. The James Webb Telescope is set to launch in 2021 from French Guiana on a European Space Agency Ariane 5 rocket. Webb's mission lifetime after launch is designed to be at least 5.5 years and could last longer than 10 years. The lifetime is limited by the amount of fuel used for maintaining the orbit and by the possibility that Webb's components will degrade over time in the harsh environment of space. An hour after its launch, the Ariane rocket will provide thrust for about 26 minutes. Telemetry from Webb begins after payload fairing separation, almost 3.5 minutes after takeoff. Webb will separate from the Ariane 5 launch vehicle a half hour after launch, and the solar array will deploy immediately afterward. Scientists on the ground would command the release of several systems that were locked for launch in preparation for deployments. In the first 24 hours, they will deploy the high-gain antenna and start the first trajectory correction maneuver by small rocket engines aboard the Webb itself. In the first week, the second trajectory correction maneuver will occur 2.5 days after launch. The first deployments are set to be the fore and aft sunshield pallets, followed by the release of remaining subsystem launch locks. The following deployment will be the telescope, after which the full sunshield deployment with unfolding and tensioning of the membranes will be initiated. At day 6, the second mirror would be unfolded along with the side wings of the primary mirror. In its first month of traversing space, the telescope would cool in the shade of the deployed sunshield and start up the flight software. By the end of that month, scientists will do the mid-course correction that ensures that Webb will achieve its final orbit. At 33 days after launch, the fine guidance sensor will be switched on, followed by the NIRCam and NIRSpec. At 44 days after launch, the primary mirror segments will be adjusted and the secondary mirror will be focused. 60 to 90 days after launch, the primary mirror will be aligned to work as one single optical surface. The MIRI will also be turned on and fully operational. By the end of the third month, the telescope would be able to capture images. Then, over the next month and a half, the telescope will optimize images captured for the other instruments and begin testing and calibration. And 6 months into the mission, Webb will begin its science mission and start conducting routine science operations. We have the rare opportunity to glimpse into the birth of our universe. And while it may not happen for some time, it is undoubtedly impressive how we, as species, have managed to create an object that is capable of delivering information from beyond a conceivable time and space. Whether or not we find a habitable planet and make it there in time, our lives on planet Earth would forever change.